guys, Mathmania back here, and let's see how we can use derivatives to find approximations of functions. Okay, so let's dive straight into it. On your screen right now, I just drew a function. Let's say that function is f of x right over there, and that's denoted by this red line that you see. So that function is f of x. On f of x, we have 2 points. So we have point P and we have point Q. So those are our 2 points, P and Q, that lie on this whatever parabolic function, if you want to call it that function. It lies on the function f of x. And another thing to note is that we have a tangent line, as denoted by this black line over here, that is tangent to point P. And the coordinates of point P is x and y. So we're just doing generic. We're not having any example numbers. It's going to be really generic. Similarly, Q is going to be Q is going to be x plus delta x. Delta x, I'm sure we all know, is just the change in x, right? So in this case, I'm taking the x value of point P, which is x, and I'm adding the change in x. Hence, it's going to go to a different point. So we have x plus delta x. That is the new x coordinate of Q. And that is the same thing for y, because if x changes, y will also change when we're looking at this type of graph. So delta x is change in x values. Delta x is change in x values, while delta y is change in y values. So now that we know delta x and delta y, we're already somewhat halfway there. In order to find errors using derivatives, you need to know that there is a relation between dy, dx, delta y, and delta x. So we're already halfway done. Now let's just get in the dy and the dx part, and that's where the derivatives come in. So in this case, you could see dy is located right there. That is dy. And just to say it more in words, dy, we're going to start from point P. We're going to start from point P over here, and we're going to follow the tangent line until it reaches the same x coordinate as point Q. So if this is x plus delta x. So we're going to keep going. We're going to keep going across this point until we hit the x coordinate of Q. And in this case, the x coordinate of Q is x plus delta x. So our delta y is obviously going to be vertical because that is in the y direction. So this is going to be delta y. That's delta y. And similarly, this is just delta x. But something interesting happens when we say that delta x tends, something interesting happens when we say delta x tends to 0. And what that means is that this part right over here is getting smaller, smaller, and smaller. So whereas our graph originally looked like this, next our graph is going to look something like this. And I'm just going to draw it really hastily over here. So in this case, in the first case scenario, let's label this the first case and let's label that the second case. The first case scenario, we see that the difference between delta y and dy is a lot. We could see that delta y is a lot longer than dy. But in this case, when we're saying let x tend to 0, meaning that the spacing between point P and point Q is very small, that means that delta y suddenly decreased a lot, and so did dy, but not that much. And it's looking that they look much closer in scenario number 2 than they were in scenario number 1. Therefore, we can conclude as we decrease delta x, or the distance between point P and point Q horizontally, because we're talking about the x-axis, as we decrease delta x, delta y and dy is almost equal to delta y. And that is very important because a lot of the word problems, this box right over here is very important. A lot of the word problems will use this basically theorem because it is very important. So I'm going to label it as a theorem and say that as we decrease delta x, dy is equal to delta y. And to add even more, these are two other important theorems, but they're just derivations of this theorem right over here. So in this case, we like to say that delta x is basically dx. So this is one important theorem, and I would say it's pretty easy to memorize because in this case you're saying dy is equal to dy over dx times dx. From this right over here, we saw that dy is equal to delta y, so we just replace that over here. We let dy over dx stay the same, and in this case, dx is just always going to be equal to delta x. This will help us in our future word problems. Okay, so our first problem here we have if y equals x to the power 4 minus 10 and x changes from 2 to 1.99, what is the approximate change in y? And I made a little note so that we know dy is equal to delta y as we just saw before. So in this case, we have to find the approximate change in y when you go from x equals 2 to x equals 1.99. The long route is that you find y when x is equal to 2, you find y when x is equal to 1.99, and you subtract them. That's basically how you find the approximate change in y. It's nothing like revolutionary. But in this case, we want to actually get derivatives into the mix because honestly, who wants to do 1.99 to the power of 4, right? What you're going to do with derivatives is that you're simply going to plug in the value 2, and if you know how to take the derivative of a polynomial function, then you're all good to go. You don't even have to plug in that 1.99 into x to the power 4, which would be a pain to solve. So how do we do that? Well, first things first, to approach these problems, always find delta x. Delta x is usually the easiest quantity to find, I would say. So in this case, delta x would be, so we're going from 2 to 1.99, so we're going backwards on the graph. So we're saying that, we're saying that if this was our function, something like that, I don't know, and this is 2, this is going to be 1.99. So what's that difference in x? So we do final minus initial, 1.99, and then our initial value was 2 because we went from 2 to 1.99, which makes 2 the initial value, and then 1.99 the final value. So now we have 1.99 minus 2, which is just negative 0.01. It's very important to remember that negative. So this right over here is our delta x, and that's going to be quite important. So I'm just going to box that in red because that's going to be quite important. Now let's bring our equation back from earlier. Here we have delta y is equal to dy over dx delta x. And now you see why it's important to find that delta x, because we have a delta x in the equation. So we're already kind of halfway there. We're trying to find this. We have this. We don't know what dy over dx is. Well, that's just the derivative, right? So what are we going to take the derivative of? We're going to take the derivative of y, which is what they gave us. So let's actually take the derivative of that. So dy over dx, we're differentiating with respect to x. So we have 4x to the power of 3. Derivative of minus 10, which is a constant, is just 0. So we have dy over dx is equal to 4x cubed. But we're not just going to plug this in here. Don't do that yet. We actually need to find a value, because the moment we plug this in here, we're going to get something in terms of x, when we know in reality the delta y should be an actual number, right? So in this case, what we would do, it would substitute x is equal to 2 in here. So this is basically that initial value we were talking about. Our initial value was 2 from over here. So this is our initial value. So we're going to substitute 2 in there. So substituting 2, we get dy over dx is equal to 4, and then 2 to the power 3, which is 4 times 8, which is 32. So dy over dx is 32, and that is also really important. So now we're just going to replace our quantities in this function right over here. So we have delta y is equal to dy over dx, which we found was 32. So that's 32. Delta x, we did final minus initial, which is negative 0.01. So negative 0.01. Solving this, you get negative 0.32 as the change in y. But remember, this is the approximate change in y. Keyword is approximate. It's not the exact change in y. You would get the exact change in y when you plug in 1.99 in here and actually solve for it. But it's just saying approximate. We don't really want to do 1.99 to the power of 4. So instead, we're just going to do the derivative way. Let's do another problem relating to this equation. So we have a question over here. Find the approximate volume of a metal in a hollow spherical shell whose internal and external radii, are 3 centimeters and 3.0005 centimeters respectively. So I've drawn a little figure here. This is the outer radius basically, or the outer circle. And this is the inner circle. That's what I'm seeing over here. And it's saying a hollow spherical shell right over here. So I'm sure it's asking us to calculate the volume of this part. The inside of this sphere is just going to be hollow, as it's saying. So it's asking us to calculate that part. And I know how many of us would do it. We would just calculate the volume of the outer sphere, right? And we would subtract the volume of the inner sphere. I'm not saying that's wrong, but the volume of a sphere is basically V equals 4/3 pi r cubed. You really want to put in 3.0005 into r and then cube it, especially if this is like a no calculator questions and you're just expected to put this in here. You probably don't want to waste your time doing 3.0005 to the power of 3 and then subtracting it from 4/3 pi r cubed when r is 3. Like all of that, it would give you the correct answer. But once again, this question is not asking the exact volume. It's just asking the approximate volume of the metal in the hollow spherical shell. So we just have to be a little bit near that exact value to actually consider this question correct. We don't have to be smack dab on that exact value. So in this case, we're not going to be smack dab on that exact value. We're just going to approximate it. And it's going to be way easier approximating it. So in this case, we have to use our equation, which is delta y is equal to dy over dx delta x. But in this case, there's no x and there's no y. So let's actually put this equation into a form that actually makes sense with this question. This question is talking about volume and I believe, yes, volume and radius, but this equation is talking about y and x values, which don't really fit in here. So let's actually rewrite this equation. So in this case, delta y, which is the dependent variable, that's volume. Volume is dependent on the radius. So we're going to say delta v is equal to dv over dr, because x is the independent variable and r is also the independent variable. So dv over dr times delta r. So that makes a bit more sense in the context of this situation. This question has volume and radius, not x and y. So in this case, we could just erase this equation and let's pull this up. So this is going to be our main equation. These two equations actually are going to be our main equations because the volume of a sphere is V equals 4/3 pi r cubed. And let's actually find delta x first. Excuse me, not delta x, delta r. So what's the difference between the r values? So in this case, delta r is going to be 3.005 minus 3. And here's why. Delta r is going to be this thing right over here. That's delta r. So what we could say is that in order to get this, another way you could think about it is saying 3 plus delta x is equal to 3.0005. This delta x is this right over here. That's delta x. So we're doing 3 plus that delta x, which will give us 3.005. And that's where we get our delta x or delta r. Excuse me, I should be saying delta r. But in this case, either way, delta r or delta x, they're both the independent variable. That will give us 0.005, centimeters. So that's delta R. We have already found this part, so that's pretty good. Now we have to find dv over dr. In that case, let's do the derivative of this equation right over here. So that's dv over dr. We get 4 pi r squared. And let's substitute r is equal to 3. So we have 4 pi r squared equals, well, that's 9, so 36 pi. So that's dv over dr. Finding delta V, since that's what they're asking us the approximate volume of a metal in a hollow spherical shell. And that's the change in volume. And let me explain why. Because if you do this the regular way, let's say you find the volume of the outer sphere and then you find the volume of the inner sphere, you're finding the change in volume. You're doing the outer sphere minus the inner sphere, which is change in volume. So in this case, we're also finding change in volume. So in this case, change in volume would be delta V, and I'm going to replace dV over dr by that 36 pi we found. And then I'm going to replace delta R with 0.005. Therefore, delta V is equal to 0.018 pi centimeters cubed, because we're talking about volume. Centimeters cubed, and that is the change in volume. Alright, so that is it for this video. So if you want more videos like these, please feel free to subscribe and like this video. And if you have any questions, just put them in the comments below. I'll be more than happy to answer them. And yeah, stay tuned to Mathmania. Bye!